What's up, guys? Nitty-Gritty Maths here, and today we're learning about discontinuities. And to start off, a discontinuity is where the graph is not connected. So, and you'll be asking yourself, why wouldn't the graph be connected? Because there's something that the equation has that doesn't satisfy that domain. So, here's what I'm saying. There's three types of discontinuities. The first one is an asymptotic discontinuity. Okay, so that type of asymptotic discontinuity is it's when your graph here, we'll call f of x is equal to x plus 4 over x minus 1, x plus 8. Alright, and that's your function, and you'll see at x equals neg 8 here, and at x equals 1, there will be a vertical asymptote, and we'll say our graph goes like that. That's our graph, and right there. So right here, we'll use a different color. Right here is our vertical asymptotes, and here there are no values defined for those. So as x equals 1 and x equals negative 8, there's no values, and so that whole line here, that it's all undefined. And that's the first type of discontinuity you should know. And there is a limited domain, so restrict the domain here. So say x is equal to all real numbers. All real numbers are denoted by a capital R, but x cannot equal positive 1 and negative 8. And that's the first type, the asymptotic discontinuity. So another type, you might have heard of it, is a removable discontinuity or a singularity. So a removable, you already know this about discontinuity, so I'll just write removable. And we have a function here, f of x is equal to x squared minus x that over x minus 2. I mean, you would never get a question like this that would give it to you like that. They would either give it to you like this, and then you would have to factor the top to get the cancel out with the bottom. But looking at this, you can cancel out this, and whenever you can cancel something, that means before you actually graph it, that means that's a removable. You in the graph itself, when you graph it, it will only leave the x squared, but when at x equals 2, there will be there's no answer there. It's undefined, so you need to draw an open circle there. And that's why there's as the answer here, if you have to label coordinates with 2 and does not exist, is undefined for that point, but it's removable. You can take it out from the function, and you can still have it somewhat continuous. It's not continuous at this point, but it's continuous everywhere else. It's not like that vertical asymptote from the asymptotic discontinuity. So one more we have is a jump discontinuity, and it's usually denoted by a piecewise function or jump discont. So I'll show you right now. So we have a piecewise function here where f of x is equal to, and we'll use a big bracket, x squared, x less than 1, and 2 minus x is greater than 1. And the reason why they do this is just because the domain doesn't match up, and the piecewise function here, when we draw it out, it will be continuous, but it's not going to be differentiable everywhere. So at x equals 1, we'll have a value of 1 here. The graph is linear from there, and it's exponential from here. So we can see there, this is a piecewise function. It's a jump discontinuity, so a jump discontinuity. And this one isn't a jump, but it's just piecewise function, where we see a lot of piecewise functions, they usually ask you to differentiate this or find a value that satisfies the continuity. So if this was, we'll say x less than c and greater than c, then we would just solve for the answer, and we would get x equals 1. And that's what c is there. So they just gave you c there, and this value would be c as well. But the main jump discontinuity is in this piecewise function. Just showing, warming you up with the piecewise function there is x squared, x less than 1, 6 minus x, x is greater than 1. So here you can see that the values, when you use the same concept from the example before from the piecewise function, it will have the parabola here at 1. So it'll have the parabola here, but it will have a higher value at 1 for this part of the graph, 6 minus x. It will go like this. So this is a jump discontinuity. You're jumping in the graph, and that's when the function approaches two values, and that's when you have to use limits, and you're going to figure out that the limit of f of x as x approaches 1 does not exist because of this jump discontinuity. Because the left-hand limit will be 1 and the right-hand limit will be 5. So that's why these discontinuities are a big topic in part of the limit curriculum as well when we do calc, and because if we have that removable discontinuity that makes our function does not jump, and I'll show you here, we'll use that same question. There's a removable discontinuity there, and the limit as x squared minus 2 over x minus 2, as x approaches, we'll say 2. Well, these cancel out, and we'll get x equals 4, even though the value here is 4 and 2. This is not defined, but the limit here is 4 because we're approaching it from the left hand side and the right hand side, and the limit is 4. Yeah, so that's the end of this video, guys, on discontinuities. I hope you enjoyed, learned some more stuff about discontinuity, and as always, nitty gritty out.